So we've already talked about one-way between groups analysis of variance. And now we're going to talk about a little slightly more complicated situation. It's called a factorial ANOVA. And for these, there's more than one independent variable or a grouping variable. So if you have two grouping variables, you'd have a two-way ANOVA. If you have three grouping variables, you have a three-way ANOVA, and so on. Also, another critical feature of these ANOVAs is whether they are within subjects or between subjects or between groups or whatever. So this is like within or like a repeated measures t-test or an independent samples t-test, right? So here each participant is in one group or condition. Within subjects, here each participant is in all groups or conditions. And it's possible with a two-way factorial ANOVA or a three-way that you could have another situation which is called mixed, where there's at least one variable that's between subjects and at least one variable that's within subjects. I'll call those independent variables. Those are the grouping variables. So each variable is either within or between, but for mixed you have one variable that's within and one variable that's between, at least. You could have more than one of each of those. When you're naming an ANOVA, you indicate whether the variables are within or between and how many independent variables there are by saying how many ways, how many independent variables. So if I have two variables and they're both such that each person is in only one condition of each variable, that would be a two-way between subjects ANOVA, or analysis of variance. And this is the simplest kind of factorial ANOVA, so we're going to start with that. And when we're done talking about factorial ANOVAs, the between subjects version, we'll talk a little bit about within subjects ANOVA, but I don't even think we'll talk about the three-way or more complicated versions of ANOVAs for this class. Next, I want to introduce a factorial ANOVA with a pretty simple scenario. And what this research is doing is looking at whether or not caffeinated beverages increase alertness. And so there's a decaffeinated and a caffeinated condition. And also we have male and female participants. So our two grouping variables are the kind of drink and gender. So this will be a two-way because there's gender and drink as two grouping variables. It's between subjects because each person only is male or female, and each person only gets caffeinated or decaffeinated the drink. If we would have done it differently and had everybody do the caffeinated drink and the decaffeinated drink, this would be mixed because there'd be a between subjects factor and a within subjects factor. But we're going to keep it simple for this, and we'll do both variables between subjects. And it is going to be an ANOVA. So what I'll do is I'll draw the results here. So we got men and women. This is their outcome variable. This is alertness. So we're trying to see in this research if caffeine increases alertness. That's our research hypothesis. And we're wondering if this effect differs for men and women, because previous research has shown that women are more sensitive to caffeine than are men. So for our results, let's see here. Men, on their alertness measure, the men who drank decaffeinated coffee, on average, let's say there's 100 people in each of these bars. So on average, the 100 men who were in the decaffeinated condition, their alertness measure was 2. So maybe we'll say they detected two hidden objects or something like that. And women in the decaffeinated condition, on average, these 100 women, their alertness was 3. And for men who drank caffeine, they did better on this alertness task. They identified 4 of those objects. In women, they, on average, the 100 women in this group had a mean of 5. So overall, it looks like caffeinated women did best on this alertness task. So it suggests that they benefited the most from the caffeinated beverage. All right, so for a two-way between subjects ANOVA, there's going to be what are called main effects and in this case, one interaction. So for the main effects, the first main effect, let's say main effect for gender. For that, what we're going to do is see if ignoring the caffeinated conditions, if men and women differed on how alert they are. So we could actually redraw this. No, here, I could show you the null hypothesis first. This will have its own null hypothesis. It's just that the alertness for men is going to be the same as the alertness for women. So this is very similar to an independent samples t-test. And in fact, what we're going to do is we'll draw this again, and we're going to have men on one side and women on the other again. This will still be alertness. 0, 1, 2, 3, 4, 5. And now for men, what we're going to do is we're going to ignore which condition they were in. And for this example, we're going to say all 4 groups, men decaf, men caffeinated, women decaf, women caffeinated. We're going to say all 4 groups have the same sample size, 100, to keep things simple. So that means that for averaging across caffeinated and decaffeinated, the average of 2 and 4 is going to be 3. So for men, if you ignore the caffeinated condition there, mean was 3. And for women, if we're ignoring the caffeinated, the beverage condition, their overall mean is going to be 4. So we're going to assume that there's really high statistical power here, and any observed differences are such that we can reject the null hypothesis. Right? So in this case, we would say that there's a significant main effect for gender, such that women are higher on alertness than men. So the next thing, and if we were doing this with SPSS, it would give us a p-value specifically for the variable of gender, and we'd just compare that p-value with alpha, and if p is smaller than 0.05, we'd reject the null hypothesis, and then we would interpret it just like we did. So the second main effect in this is the kind of drink people had, caffeinated or decaffeinated. And we could draw that as well. So this is still going to be alertness. But now we're going to average across gender, so we'll put decaf over here and caffeinated over here. And so for our decaffeinated, right, so that's a 2 and a 3, and there's 100 people in each, so we could just average these together. That's going to be 2.5. And for caffeine, that's 4 and 5, average those together. That's going to be 4.5. So what this shows, and again we're assuming that we have very high statistical power, any differences are significant, we can reject the null hypothesis. Which the null hypothesis here would be the average alertness for the decaf equals the average alertness for the caffeinated, right? But in this case we reject the null hypothesis, and we find that people who drank caffeinated beverages had a higher alertness score on average than people who drank the decaffeinated beverage. And then there's those are both main effects, so there's always one main effect per variable. So if you have a two-way ANOVA, there's two main effects. If you had a three-way ANOVA, there'd be three main effects. So if we had gender, drink, and year in school, freshman, sophomore, junior, senior, that would be a third variable, and that would have its own main effect if we had that in there. So we have the main effect for gender, main effect for drink, and then we have the interaction. So this interaction is a new concept that we haven't talked about yet in this class. And the idea here is if there's an interaction, then the effect of one variable differs across the levels of the other variable. For example, if caffeine increased alertness more for women than it did for men, then there would be an interaction. And the way you can tell if there's an interaction, there's a few different things you could do. So one thing we could do is they're all mathematically interchangeable. So one approach would be to see how much did women get a boost in their alertness from going from decaf to caffeine, right? So that's the difference between the height of these two bars. So for women, their alertness was boosted 5 minus 3 was boosted 2. So the effect for women was an increase of alertness for 2 from going from decaf to caffeinated. How about for men? Well, they went from a 2 to a 4 also, actually. So for men, there was an increase in 2. So both men and women had the exact same increase, the exact same effect from caffeine. So in this case, we would not reject the null hypothesis. We would say that there's no interaction. Or the interaction is not significant. And here the interaction is actually just that the null hypothesis is that there's no interaction. There's a nice mathematical way of expressing it that is commonly used. So one way you could detect these interactions is by calculating these different scores between 4 and 2 and 5 and 3. But another way to do it that's pretty easy is if you draw for the decaffeinated condition a bar right across the middle of these two. So we'll draw that bar there. And then if we draw a bar across these two bars, I'm doing middle to middle here, doing my best. If these two lines are parallel, well, that tells you that that this boost here is the same size as the boost here. It's actually mathematically, like I said, all these approaches are mathematically interchangeable. So this says that for the caffeinated folks, right, there's one difference between men and women, and for the decaffeinated folks, there's one difference. So the differences were the same. So if the lines are parallel, no interaction. You can even draw it this way too, another way, which won't look great on this particular graph, but you could do it this way too. You could draw these two lines. Put this back here. You draw those two lines, and if those two lines are parallel, there's no interaction. So they're all mathematically interchangeable ways of drawing it. Let me just change the results just a little bit so that we can see what it would look like if there were an interaction. So we'll keep most of these the same. All right, so now we'll keep red is still decaf, blue is still caffeinated. So now what I've drawn is a situation where women had a greater improvement than did men from drinking caffeine. So you could draw it this way, right? So from 3 all the way up to 6, so women got a boost of 3, whereas men went from 2 to 4, they only had a boost of 2. And again, we're saying that there's a lot of statistical power here, so any differences are significant. Although in reality, again, you'd look at the p-value on your computer program's output to the side, and there's a p-value for each main effect and one for the interaction. And so that's how you'll actually decide if there's a significant interaction or not. But in this case, it's drawn intentionally such that women had a greater increase in their alertness from caffeine than men. Right? So here we saw that women did better on alertness regardless of caffeine. Here we saw that regardless of gender, caffeinated people did better than decaffeinated people. And with this kind of output here, with this kind of results, what this shows is that women would benefit more from drinking caffeine on their alertness than would men, whereas the previous version where there's no interaction, it didn't matter if you were a man or a woman, either way you got a boost of 2. And so for this interaction rate, so you could calculate these difference scores. Another thing you could do is draw these lines. Right? And I'm trying to draw them so you can hopefully see that they're not parallel. In fact, if you just continued them, before long they would cross over, right? So not very close to parallel in that case. And this drawing the lines connecting the bars is the approach that I like to use when I have a bar graph to figure out if there's an interaction or not. All right, so now I want to talk a little bit about why a researcher might want to use Factorial ANOVA in their studies. So why would you use a factorial study where you'd have to do these kinds of more complicated statistics? One reason is to see if there is an interaction. Right, to see if the effect of caffeine is the same across men and women. And it turns out it's pretty common for men and women to differ on a lot of variables. And so you might just not know if there's a difference between the two, and so you might want to just include men and women in your study. And then if you do have men and women in your study, but you're interested in caffeine versus decaffeinated drinks, well then you can check to see if the effect of caffeine differs across men and women. So you can just see if there's an interaction there or not. Sometimes you might do this strategically to see if your results generalize. And that means if they apply to another group that you haven't looked at previously. So let's say if you do a study initially where you just have men, they come into the lab and they drink decaffeinated coffee or caffeinated coffee, and then you measure their alertness. And you find that caffeinated men are more alert than decaffeinated men, so not too surprising there. Then you do another study where you want to see if this effect generalizes to women. Does caffeine also increase alertness for women? So you could do another study where you have men and women come into your lab and then do the same caffeinated versus decaffeinated conditions and see if the results for men generalize to women. And you could even do this across cultures. If you, for example, have Americans for one of your, as one of your groups, you could compare them with Australians or people from another cultural or national group to see if your results generalize from one group to another. And another reason you could do factorial ANOVAs is to look for moderators. A moderator is a variable, let's say, that moderates. I'll explain what I mean by that in a second. The effect of one variable on another. So when you're doing a factorial ANOVA, if there is a moderator, you'll have a significant interaction. So write a variable that moderates the effect of one variable on another. So the way I drew this with a significant interaction, the moderator is a variable that's like conceptually you would expect for people who are different levels of it, like for men and women, right? Let's say I think that women are going to be more sensitive to caffeine because of previous research that shows that they have a greater increase in their physiological arousal, measured like, maybe with blood pressure or something, after drinking caffeinated versus decaffeinated coffee. So women have a bigger effect physiologically from caffeine drinking than men do, right? So in that case, there's already a gender moderated the effect of caffeine on physiology. And here I might expect gender to moderate the effect of drinking caffeine on alertness. So that means that I think that for men and women, caffeine will differentially affect alertness like it did with the 3 versus the 2. That is a differential effect because women had a bigger increase in alertness than men did. So a moderator is a variable, like gender, that moderates the effect of another variable on the outcome variable, like how much caffeine increases alertness. So these moderators are always associated with interactions. Okay, and another nice thing about factorial ANOVAs is they let you know, they let you see the effect of the independent variables, the grouping variables, separately. So specifically, they give you these main effects separate from the interaction. You can still see if alertness differs for men and women, or if alertness differs for caffeinated and decaffeinated. So these things, you get this information in addition to whether or not there's an interaction, right? So these factorial ANOVAs give you a lot of information to work with.